In this video, we'll look at what happens to a regression slope estimate when we add another explanatory variable to our regression. So we've done some examples already looking at rural-urban wage differences. And what I've done here is the first regression on this slide is a regression of log hourly wages on a rural indicator. This is using a sample of about 25,000 people in North Carolina observed in 2022. All right. So the way to interpret this is people in rural areas earn 20-something% less per hour compared to people in urban areas. That's just in the simple regression. Now, what happens in the multiple regression if we control for years of education? Okay. When we control for years of education, you can see the coefficient on the rural indicator changes quite a bit. So that rural-urban wage gap drops in magnitude from 23-24% down to about 14%. Again, those are just approximations, okay? But you can see that it's a substantial change there, all right? And so in general, controlling for a new explanatory variable, moving from one regression to another, adding an explanatory variable, here education, will in general change the coefficients on existing variables like the rural indicator, sometimes to a large degree, okay? And we're going to study a framework that enables us to understand, to sort of think about why these changes occur the way that they do, okay? And in that framework, it's going to turn out that the two things that matter are how the new variable is related to the existing variable. So what are the rural-urban education differences in words here, all right? And then how the new variable is related to the dependent variable. Okay, here's the framework. There are three regressions. The guiding question here is how does the coefficient on the explanatory variable x1 change when another explanatory variable, which here will be x2, when another explanatory variable is added to the model. We have a short regression of y on x1. We have a long regression of y on x1 and x2. And you can see how that fits our wage regressions on the previous slide. Y is log wage in that example. X1 is the rural indicator. X2 is the education, years of education variable. The auxiliary regression is there to reflect how the two explanatory variables in the long regression are related to one another. So this is a regression of the new variable on the existing variable. That would be education on the rural indicator in the example that we just saw. Okay. So there's a lot going on here. There's parameters beta in all these models. I made the auxiliary regression parameters delta. Okay. And to distinguish the betas and the error terms in the short and long regressions, we've superscripted things S or L as appropriate. Okay. This, or equivalently this, shows us how some of the estimates of these parameters are related. So there's four things that we're going to focus on. Remember, the guiding question is how the coefficient on x1 changes. So we're interested in how those beta 1 hats, are related to one another. And the difference in those beta hats depends on our estimate of that beta 2 hat and this slope from the auxiliary regression. Okay. Remember, in this auxiliary regression, x2, just think of it as the new variable you're adding in the long regression, and think of x1 as the existing variable, all right, that was already there in the short regression. All right, now the formula says this. This is the estimate in the short regression. This is the estimate on x1 in the long regression. So think of those as the two coefficients on the rural indicator, all right? And then this is the product of these two things, right? And sometimes it will be better to maybe move this term to the other side and have this version of the expression. You can see that they're identical. It's just a question of which one we think is more illuminating in a particular context, okay? This is the difference between the coefficients on x1, such as the rural indicator. And remember I said that the change in the estimates depends on two things. It depends on how the new variable, education, is related to the existing variable, the rural indicator. That's being picked up by the coefficient delta 1 in the auxiliary regression. And the other thing that matters is how the new variable is related to the outcome. So like how education is related to log wage, okay? And that's being picked up by the beta 2 hat, which is an estimate of that parameter, okay? We're not going to formally justify this. I just want to kind of show you an analogy for why this formula looks the way it does. Okay, go back to the model. Imagine holding u fixed. Okay, let's imagine we're thinking here of the long regression model. All right, so holding the error term fixed in the sample, which is, remember, you run this regression using the variables y, x1, and x2 in the long regression. In the sample, think of y log wages as a function of x1 and x2. And remember that x2 is going to be related to x1. There might be some correlation between the two. Okay, so let's write out the total derivative of our of y, the outcome variable, with respect to x1. The total derivative is this. There's a partial effect of x1 on y. And then there's a relationship between x1 and y that runs through x2. So this is the partial derivative of y with respect to x2, holding fixed x1. And this is the derivative of x2 with respect to x1. So this term as a whole right here is saying when x1 changes, x2 may tend to change because of correlation between them, and x2 has its own partial effect on y. Okay, and then if we try to map these things onto regression estimates, the simple regression slope here is just picking up the total relationship empirically between x1 and y. This partial derivative is holding fixed x2. All right, so it is an estimate of the long regression slope on x1. Similarly, this is partial y, partial x2, holding fixed x1, so it's an estimate of the slope on x2 in the long regression. And this is like an unconditional relationship between x1 and x2. That's coming from the slope in the auxiliary regression right here. Okay, now if you don't know multivariable calculus and this didn't make any sense, that's okay. I'm not going to ask you to reproduce it, but if you could follow it, hopefully it gives you some sense of why this relationship looks the way it does. Okay, I do expect you, of course, to be able to work with this relationship. You're going to see a bunch of examples and problems about that. All right, just a few notes before we wrap up the video. So why do we use this framework? This shows up a lot in empirical practice. It's very common. We estimate a regression, and then we say, well, what would happen if we controlled for some additional stuff? Okay, so we re-estimate our regression, and maybe our results change. We need a way to think about those changes. Okay, so that's the first bullet here, is we control for some new explanatory variable, and we want to understand why did the coefficients on the existing explanatory variables, like the rural indicator, change. Okay, we can also use this framework to think about, well, what if we would like to control for something that we think differs, maybe between rural and urban areas, but we don't have a good measure of it, or we don't have a measure of it in our data. Okay, then we could at least use the framework to maybe make a prediction about how the coefficient on x1 would change if we could control for some explanatory variable. All right, and both of these things get used a lot in applied economics. Okay, a couple further notes here. The whole framework still holds together if you have another explanatory variable that's added to all three of these. Okay, so you can imagine there's some other variable x3. So like we start with a short regression with 2 variables, we go to a long regression with 3 variables. All right, and the auxiliary regression would be a regression of the new variable in the long regression on the 2 variables from the short regression. Okay, and you can still use this framework to think about how the coefficient on x1 changes, and it's just, remember, conceptually, it's this change right here is the product of the coefficient on the new variable in the long regression, and then the coefficient on x1 in the auxiliary regression. Okay. Now, could it be that you add an explanatory variable and the slope on x1 doesn't change? Yes, there's a couple of cases that don't come up a whole lot, but sometimes. But yeah, that can be true. All right, you can see that the difference between those beta hats is this product. So for these things to be equal, that product, beta 2 hat times delta 1 hat, needs to be 0. All right, so this can happen if delta 1 hat is 0, all right, or of course if the beta 2 hat in the long regression is 0. Let's try to put that into intuitive terms. So this being 0 means you regress the new variable on the existing variable and the slope is 0. So this is the case where the variable you add to the regression, like education, isn't correlated with the existing variable, the rural indicator, for example. Okay. In that case, then you can control for the new variable, but it won't change the coefficient on the existing variable. Right? This is the case where you add the new variable and its effect, like conditional on x1, its association with y in the long regression is 0. Okay, so effectively you've added a variable that doesn't matter, or at least doesn't matter conditional on having included x1. All right, that's a less common case. This case does actually come up in the analysis of experimental data. All right, so that's the framework.